All right, class, today we're doing properties of rational functions. I'm going to skip this part and go right to parent functions, but rational functions give you something that looks like this. You should have seen it before, so you should recognize some of the things in there. But let's talk about this parent function. When you see just 1 over x, this is also called the reciprocal function when we did the library. It has a vertical asymptote, if you remember vertical asymptote, at 0 and a horizontal asymptote at 0. So the parent function goes through the point 1, 1. 1/2 is at 2 and 2 is at 1/2. And then it also does the same thing over here with the negatives. So this is the parent function 1 over x. Now, the parent function of, and also there can be shifts with this. So it's x minus h plus k. So that's how you can shift a point. This is the horizontal shift. It's the opposite again. And then the vertical shift is the plus k on the outside. Again, the domain for something like this would be x cannot be 0. The range, y cannot be 0. For something like this, when it's squared now, just like even and odd for zeros, you get even and odd. And we'll talk about this a little bit later with in the notes. But right here, the only thing that's different is this piece stays the same, well, except for the numbers are a little different. But this piece now flips up and is also positive because it's squared, so you'll never get a negative y. Also, since it's squared, this is even. Notice how at even they go the same direction, where odd they didn't. We'll talk about that later. The same thing happens with transformations. And the domain is that it's all real except for x cannot equal 0. Now the range here is that y has to be bigger than 0, or you can write that in interval notation because it's not going to hit 0, but it's going to only be positive values. Okay. Now finding domains, you get the domains from setting the bottom equal to 0. We've done this a lot already. So if we set that equal to 0, we get x, we have to factor, so 3 and 1. So we get x equals negative 3, x equals negative 1, which means my domain for this problem is that x is all reals except for it cannot equal negative 3 or negative 1. Okay, so that's my domain. Now, some important properties for these. You can have asymptotes, you can have holes, you can have y and x intercepts. So to find a point of discontinuity slash hole, they're called the same thing, you need to factor and simplify. This factors into x minus 4x plus 1 over x minus 4x plus 2. Notice how these two things cancel out. That is where your hole is. So x equals 4 is the x coordinate of the hole. The simplified version of this function is x plus 1 over x plus 2. To get the y coordinate, you plug the x into the simplified for the y coordinate. So for y, we get the y coordinate is equal to 4 plus 1 over 4 plus 2, which is 5, 6. So there is a point of discontinuity at 4, 5 over 6. Okay, so that's where you can get your holes from. Whatever cancels on the top and bottom, that's the x value where there's a hole. X-intercepts, where it crosses the graph, we've talked about that. That's in the form of x, 0. And how do you do that? You set y equal to 0. Now, generally, in rationals, it's you're setting the top equal of the fraction equal to 0, generally, unless there's another constant. So here, the only way the y is going to be 0 is if the top is 0, because if the bottom's 0, it's undefined. So we set the top equal to 0, and we get x equals 3. And just like, so our x-intercept is 3, 0, and since it's a factor of 1, or it's odd, so we say it's odd, that means it crosses. Just like it did last chapter, or at the beginning of this chapter, I should say. The y-intercept is in the form of 0, y, which means we put zeros in for all of the x's and solve for y. So 0 minus 3 over 0 minus 1 and 0 plus 3, which is negative 3 over negative 1 times 3, which is 1. So we get that the y-intercept is 0, 1. Okay? So vertical asymptotes are a line where x is undefined. So we get them from our domain restrictions. So that's where we look at our domain. But we don't look at the crossed out ones, because the crossed out ones give us the holes. So we would say x equals a number. And again, you set the denominator equal to 0 and solve. So for down here, we have these two things are equal to 0. So we get x equals 1 and x equals -3. So that's, and since nothing canceled, these are both my vertical asymptotes. They are both odd, because again, they only are at a power of 1, which means that at the vertical asymptote, it's going to look like that. One way it'll go up to positive infinity, one way it'll go to negative infinity. If it was even, it would look like 1 over x squared, where it would both go in the same direction. All right, domain and range. Again, if I give you some graph, I'll put something at like 3, and then a horizontal asymptote at like -2. So if I gave you some random graph here, again, the domain is all the x values, and the range is all the y values. So for this graph here, we would say the domain is that x cannot be 3, and the range is that y cannot be, what is it, -2. Now, once in a while it can be, it could be all real numbers for range, but we won't look at those today. Finally, we have the horizontal/oblique asymptote. Okay, it describes the end behavior of the graph. It's in the form of y equals a number, because it's horizontal, or the oblique is a line, so it's y equals mx plus b. How to find it? There are 3 ways to find it. You have to look at the degree on the top and bottom, the highest degree. Okay? If they are the same. So if we look at this example, it says 2x squared is the highest one, 3x squared, then it's the ratio of the leading coefficients. So we would just say the horizontal asymptote is the ratio of the numbers in front, which happen to be 2/3 here. And that's it. If they're the same, the highest powers are the same, that's what you get. If the degree on top is bigger than the degree on bottom, such as this one, we're going to use synthetic division to find the actual asymptote. So, this is what I'm dividing by, which is a 0 of 3, and I'm dividing this top thing. So this top quadratic, 2, 3, -1. When you do this, it does not matter what your remainder is, because you do get a remainder sometimes. 9 times 3 is 27, and we get 26. Well, the remainder doesn't matter. This matters. So we would say that the oblique, or slant, is the equation y equals 2x plus 9. And we'll look at that tomorrow with graphing, how that looks on the graph, or maybe the next day. Now, if the degree on top is less, so that's bottom heavy, then this piece basically goes to 0, and it's just equal to whatever constant you're adding to. So if there is no constant, it's equal to 0. But since there is a constant here, this would be y equals 3, because this piece goes to 0 pretty much when it is bottom heavy at the ends of the graph. So that is a slant and horizontal asymptote. So now we're going to do some examples. It says for each rational function, list all of the transformations. So again, there are 3 here. We start with the horizontal transformation. I would say that it is right 3. Then I would say it's a vertical expansion or a stretch by 2. And then this is the horizontal, so I'd say, or sorry, vertical, and it's a vertical shift. I don't know why I said vertical shift. I could have just said shift up 1. Okay. So when you're graphing this, you can kind of just figure out where those points were going to be. So 1, 1 moves, well, think of the asymptotes actually. If you move the asymptotes, they were at 0 and 0. Well, now, the x asymptote is at 3, the y asymptote is at 1. And it's stretched. It's really hard to make it look stretched though. So you can just kind of sketch it like that. That's really all you have to do is look for where the asymptotes go. So that's A. B, it says graph it. That's B. Use the final graph to define the domain and range. So C, once we have the graph, the domain is that x cannot be 3, and the range is that y cannot be 1. And then D, we would say that there is a vertical asymptote when x is equal to 3 and a horizontal asymptote when y is equal to 1. Because it was bottom heavy, so it's just 1. So this one here is the other parent graph, x squared. All that's happening here is there's a reflection. So 1 would be a reflect over the x-axis because of the negative. And then a shift up 4. So if we graph that real quick, this stays the same, and then 1, 2, 3, 4. So since it's reflected, it's going to look something like this because it reflected over. It's always going to be negative. So that's what happened to that graph. C, the domain, is x cannot equal 0. The range, though, is that y, it has to be less than 4. Hopefully you see that because 4 is the highest it'll go, but not include. And then D, we have a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 4. Okay, and no obliques. Okay, let's keep going. Down here we just have to list vertical, horizontal, or obliques. So first thing I like to do is just get the verticals out of the way. The verticals happen when the bottom is equal to 0. So x equals -4 is the vertical asymptote, as long as it doesn't cancel. So that's the vertical asymptote for this one. The horizontal, we look at the degree. So if I look again, this is an x to the first, x to the first. So we look at the ratio of the coefficients, and we get y is equal to 3 over 1, or y equals 3, which is the horizontal asymptote. Okay. For this one, again, let's start with the bottom being 0, so we get, because that's going to actually come into play here with the next thing. So we get 3x plus 5 equals 0, so I get x is equal to -5/3. And that's my vertical asymptote. Now for the horizontal or oblique, if we look, the power on top is higher than the power on bottom. So since that's the case, we have a slant. So we're going to do synthetic division. Now the reason why I did the vertical asymptote first is that is what we're going to divide by. Okay, so we're going to do that really quickly. 6 times 5/3 is -10. This is a -3. This is going to be positive 5. Okay, so this one actually has a remainder of 0, which doesn't matter. So this oblique is 6x minus 3. All right, I'm running out of time here, but the good news is, let's check this. I might not be able to finish these two, but I'll do one of them. If there are any holes, and then x and y intercept. So there is a hole at 2. When x equals 2, there's a hole. If you plug that back in to the remaining stuff, you get 5 over 1. So that the hole is at 2, 5. The x-intercept is when y equals 0, so when 0 equals x plus 3 over x minus 1. Remember, you set the top equal to 0, so that's at x equals -3. So the x-int is at -3, 0. The y-int is when x equals 0, so you plug 0 in, and that equals -3. So the y-intercept is 0, -3. Okay, so we have the hole at 2, 5 because of the cancel. The x-intercept at -3, 0 because the top is equal to 0, and the y-intercept at 0, -3 because the whole we plug zeros in for x. Okay, I'm going to stop there. That should be plenty to get you guys started on the assignment. If you missed, this is just an extra example I did not have time to get to.